the bit I'd say I have trouble with is like using it with wave particle duality, so like how it proves it. Because I'm fine with the whole process of electron hits.
Okay, so what? So we can use the photoelectric effect as a proof of wave particle duality, but what specifically is it proving? Is it proving that a wave is a particle or particles are waves?
Would it be wave as a particle because it's one-to-one interaction?
Because it's one exactly. So the point is we've got waves coming in, and what is traditionally a wave feature? If you had two waves coming in like that, interference. So you would assume that you could, even though my diagram's not perfect, you'd assume that you could superimpose these and you get one bigger wave, which implies that if that interacted with something that absorbed it, like, for example, an electron, so if that got absorbed by an electron, you'd assume that would gain twice as much energy as if the individual ones had gone. But no, in the photoelectric effect, what actually happens is you have your metal surface down here, and then you've got trapped electrons underneath. Specifically, what kind of electrons are these?
Surface.
Surface electrons. Why are they surface electrons? Why does that matter?
Because they're the only ones that can be absorbed.
They're not the only ones, but
they're the ones that can be released.
It's the easiest. It's the least energy to required. So we get our photons coming in here of given energy, and exactly like you said, Seb, it's a one-to-one interaction. So this one photon that comes down here releases one electron over here, and then this photon that comes in here will release a second electron. Unlike if these were perfectly in phase, you'd assume you could make more energy, therefore you'd get one electron that shoots off with one, but it doesn't happen, so it's always directly proportional. Right, what's the formula for this? What's the formula for the photoelectric effect?
HF equals work function plus maximum kinetic energy.
Equals work function plus a half mv squared. Max. Why max? Where are you going to lose energy?
When it gets absorbed.
By what?
By the electron.
The electron's what has the potential energy. The kinetic energy, sorry. What might happen to this electron as it escapes? So we got, if nothing, okay, so if this just got released and just flew off into nothingness, then it's going to have maximum kinetic energy. What might happen to it as it escapes the surface?
Oh, it's going to get air resistance.
It could, yeah, it may bump into things. It could just, you just get energy loss to surroundings, to whatever's there, and that's the whole point of this max. If nothing gets in the way of it ever, it will have that. If it's not quite a surface electron, then it's going to have less. Do you know what I mean? It's because the work function will be slightly different if it's deeper down. So we've got HF, H being Planck's constant. F is the frequency of what?
The wave. Is it incident?
Yeah, of the incident photon. Specifically photon, we've got to say. So we've got incident photon. That's frequency F. This thing here is the work function. How do we define work function?
The energy needed to...
No.
Oh.
Well, okay, so yeah, go on. It's the...
Minimum energy.
Yeah, that's normally what they say, isn't it? So it's the minimum energy required to do what?
Cause an electron to be released.
Yeah.
You've missed out a word. What's the word you missed out? To release a surface electron. Alright, so it's the minimum energy required to release a surface electron. The reason this is a proof of waves acting as particles is exactly like you said, Seb. It's a one-to-one interaction. Ooh, if I can fit it on. It's a one-to-one interaction. One wave, one photon reacts with one electron, or is absorbed by one electron. So it's one-to-one interaction. That is usually a particle property. So you get this, and then obviously M, they won't necessarily tell you M in the question, but what is M going to be every time?
9.1 times 10.
Oh, but what is that?
Oh, the mass of an electron.
This is the mass of an electron, because it's an electron that you're releasing. And MV, whatever, fine. So, what sort of questions are they going to ask you for this?
One that's come up in the last papers has been to simply explain first how you would prove the photoelectric effect, and then
how you'd use that to prove that waves can act as particles.
Okay, so
which
Going
is
back.
essentially-
So effectively is what we just said.
Yeah.
So you get a metal surface, you shine photons of known frequency is the key. That you know the frequency that you're shining on. What's going to happen if the frequency is too low?
nothing will be released.
Nothing releases, so what happens to the metal?
It just heats up.
Just heats up. So if you shine infrared light, for example, on a metal surface, no electrons get released, so the particles just start vibrating faster, therefore the surface heats up. Whereas, if this is above the threshold frequency, then you're going to ionise the metal, you're going to get electrons released, etc. All right? Normally they'll put this in a circuit, and they'll say, or they could put it in a circuit. So if I draw a metal, here's a metal surface, here's, oh god, that's awful. There's a detector, and we say, well, let's say we're going to put some incident photons, we're going to shine some incident photons onto this surface here, and it's going to release electrons. So if you shine 2 in, you're going to get 2 electrons going in. How can we double the current? How can we double the photoelectric current?
Double the intensity.
No, the frequency. No, the amount of photons.
Double the number of photons. So if you've got 2 electrons coming off here, let's say, for example, let's say putting this amount of waves in gives you 2 amps. If you want 4 amps, you'd need to double the incident photons. Yeah? So you need to increase current, your number of photons needs to go up. To increase the voltage, so to increase the amount of energy they have going through, how are you going to do that? How are we going to increase the voltage? So how am I going to increase the energy that each of these electrons has?
Increase the frequency.
Yeah, why?
I think it's the formula.
Because of what formula?
HF equals work function plus
Oh, because if you
max.
increase the energy, if you
Yeah.
increase the frequency, you'd increase the energy.
By increasing frequency, that stays the same, that stays the same, half doesn't change, m doesn't change, so what's the only thing that's going to go up? The V, so the kinetic energy, so the energy that's left in the electron afterwards. It's not going to be, if you double voltage, sorry, if you double frequency, voltage doubles, because what? Because if you double the number of photons, you do double the current. Why don't you get double the voltage if you double the frequency?
Because the voltage, the speed is squared. So
No, not
Because
necessarily.
you're adding the work function.
Because of the work function, because of this bit here, which is like a remainder. So if that was 2 and that was 1 plus 1, well, if I double that to 4, well, I've still got 1 there, but I need 3. I'd have 3 left over there. Do you see what I mean?
no.
So actually, by doubling the frequency, we've got over double the energy left over, because you've lost a bit of it in releasing it in the first place. All right.
Okay.
What's the other thing they sometimes say? They talk about this intensity. What's the formula for intensity?
I can't remember what type of intensity it is, but it's intensity plus cos squared theta.
No, not that formula. Different one. What's the formula for intensity?
It's the number of say, electrons per square area.
Right. So if I were drawing this as a diagram like that, and I've got this amount of photons coming in, what are we saying? So it's going to be per unit cross-sectional area. And if you've got a number of photons hitting a surface in a second, how do we describe that? What do photons have? What are photons?
Packets of energy.
Packets of energy. If you've got that many packets of energy hitting something in a second,
So it's energy per second.
it's energy. What's another way of saying energy per second?
I keep thinking of frequency.
Not frequency. What has the units joules per second? What's another way of saying 1 joule per second? One something is equivalent to 1 joule per second.
It's power.
What's power measured in?
Watts.
That's the one.
intensity is power divided by cross-sectional area. Have we done this? You've done this before, you should know this. So intensity is power divided by cross-sectional area. So if we have, we've got our fixed area here, and we've got power. If we double the intensity of light, what does that actually double?
Power.
It's going to, if you've got a fixed area, you double the intensity of light, you're going to double the power. If you have if you have a fixed power supply, this is a question that often comes up where they try and confuse you. If you say that your source is only 1 watt, let's say you've got 1, or something usually 1 milliwatt or something like that, but your source is 1 watt. But the question says, well, what happens if you increase the intensity? Now, how can you increase the intensity but keep your power the same?
Decrease the area.
Area is going to be the same as well.
So you want to increase
So
intensity but keep the power
how
the
can
same.
I increase intensity but somehow keep the power constant? How can I do that? What's another way of thinking of intensity? You said it earlier.
I did.
What's another way of thinking of intensity?
It's like the amount of things per second.
No, the amount of what?
The amount of photons.
So the amount of photons. So how am I going to increase the number of photons? So by increasing the intensity, what I'm actually saying is I'm going to increase the number of photons.
So each photon needs less energy.
So each photon has less energy. You would need to have less energy to keep the power constant. So if each photon has less energy, each photon's got less energy, but you've got more photons, so you're going to release more. But what's going to happen to their potential, their kinetic energy?
It's going to decrease.
It's going to decrease. Do you see what I mean?
Yeah.
That's a really obscure, sort of weird, wordy way of thinking. But if they're going to tell you things like this is fixed, what's the only way you can keep that fixed but increase your number of photons? Well, that means that the number of your number of photons must go up. Therefore, the energy of each photon must go down. Exactly like you said.
Okay.
It's weird. I wish we had a past paper question that asked, but that's it. This is quite an important formula for discussing this. In fact, the way they normally phrase it in an exam is if you take the frequency. What happens if you increase the frequency? So, by increasing the frequency,
Increasing the energy.
you're increasing the energy per photon. So technically, the intensity goes down. So it's the opposite of what we just said. That's normally what they say. They'll say two things. What effect does increasing the number of photons have? And what effect does increasing the frequency have? It's like a trick question. Anyway, so that's is there anything else photoelectric effect-y? Have I missed anything out?
No?
Okay. And what was it you wanted to look at, Josh?
That's it, really.